I think that any integrated project like this has so many elements, nonlinear elements, contributing to the final objective, that it may be near impossible to really understand the result, okay? Because there's so much interaction going on. And the more complicated the models get, the more models you integrate, the more complex the whole problem becomes. So there is not going to be a simple explanation for the result that you get. I just think you know that if you have a simple function and two variables, you can try to do an analysis. But the more complex, the more integrated, the more models you're integrating, the more variables you have, the less likely you'll be able to fully understand the optimal solution is providing to you. I think it's good to try to understand, but it may not be possible. It may just be too complicated. I don't know. Do you agree? Anybody have disagree? Or I mean, I think that's part of the nature of the beast here. You know, the equation, we do PVT, we take an equation of state and fit it to a lot of PVT data, lots of different types of data, okay? Maybe thousands of data, you know, different types, densities and saturation pressure, K values, all sorts of complex thermodynamic data. And you have an equation of state model with maybe 100 parameters, 100 knobs to turn, okay? And that we fully understand why the set of parameters ended up at a certain set to give us a best fit model. We don't go there. We don't try to understand it because it's almost impossible. There's too many parameters. There's too many data. There's too many types of data. You know, I don't think it's possible even for the best thermodynamicists to understand it. There's too much complexity to it. That I think is a problem. Will be a problem in any kind of integrated model optimization that you do. I think it's just too complicated. But you can try to assess things. Any other observations? Everybody was able to do what you wanted to do? Did you guys get everything working on that? Yeah.
The point is there is no optimization for flat affiliate because of the discount rate. So it's much more better, and we are going to produce 50%. So the best scenario is to produce everything as soon as possible. Because afterwards we have the discount rate and some decrease.
Well, what you're saying is that the net present value along the plateau time direction, variable direction, is monotonic. It's monotonic. Well, it's not. It might be linear, but it's okay. But it's monotonic. That's the key. That the shorter, the higher the net present value. Right? Okay. So that's. Did anybody else see that? That observation that. Everybody notice that? Okay. Okay. So let's just say observations. 1 is that something like that? Is that correct? Everybody found it was monotonic. Okay. And what do we get out of this? What do we conclude now that we see that? Right. Yeah. I mean, at least you can take it out for the time being. Okay. use 8 years, fix. And then if you want to study other variables, because the more variables you add, the longer the simulations take. And of course, these are very fast simulations, but if it takes 6 hours, you need to think about that on your well startup. If you actually have data, you have to find out which of the 22 variables do I want to change. You don't want to change all 22. So you can kind of eliminate this variable. Now that's for the time being, because then if you start doing optimization with 2 new variables, right, or maybe you change the model a little bit, you come to a new optimal. You might want to recheck it, bringing the time, the plateau time back into the picture, and see, well, maybe now it is non-monotonic. For example. Do you all understand what his comment was? If the gas price shoots up very high, then it may not be a monotonic.
So if, for example, you put that every year the cost of the gas is increased by 10%, then you already might have a situation that is not so good. One thing. Another thing, of course, there is a built-in assumption here that you can take as much gas as, I mean, the receiver has no limit on how much gas he can take in the rate that he takes, which is not realistic. Normally the transport system has maximum capacity.
But we don't have the transport system as part of our integrated model. If we did, then of course that would have to be.
So the only thing encounter that is that you assume that the gas price is going to increase exponentially or even linearly every year, and then
well, there's no gas price. We're assuming this now. So I think Michael's point was that if you introduce this, so for the given set of assumptions, and that's the whole thing, is that if you change anything in this model, you can't necessarily make this conclusion. For this 3 set of variables, for this set of everything else fixed, you can do this. Okay? But if you start changing things around, you may have to reevaluate whether this is in fact the case. And a good example would be time-dependent prices. Realistic, exactly. Well, what's realistic? You know what the gas price does over a 15-year period. I mean,
in the Whitson, those kids will assume that it's going to increase by 10% every year over the lifetime of the system, which is, again,
but there's never been a gas or oil price that has changed monotonically for 10, 15 years, ever. So if you know it's going to do like this, then assuming that versus, and instead of doing this versus this, I mean, I don't know. It's okay, but I think this was a good observation. But for our problem, it's the case, so we can drop this as a variable. Any other observations that you have made? Yeah?
I just made one right now. The discount factor is 0.1.
All right.
Which would be 10%.
Yeah.
But I'm not so good with economics, but 10%, it's basically the deflation of the money. So that means 10% is a bit high, isn't it? It's the inflation.
no, it's not. It's the cost of capital. If you go to the bank and you borrow, and you have the option to put the money in the bank or to put the money in the project.
Yeah.
But because the project has a high risk, so 15% sometimes is not a low. There is a high risk, so the bank puts. You basically compare what happens if you put the money in the bank.
Okay.
So 10%. It's not just the inflation.
No, but it's interest rate and
It's the interest rate, risk counted, and for oil projects it can be 25% or 20% or 18%.
Okay. Because I just reduced it, and then the plateau plateau was then 12 years instead of 8 years.
Yeah. And that's a good point, because what it essentially do, if you take it to 0 discount, I don't know, what did you change it to?
I changed it to 3% because I thought maybe the inflation rate.
Yeah, because what's the difference between having a discount factor and flat price and having a discount factor and an increasing price? Okay? If you have an increasing price and a discount factor, you essentially get a 0 discount factor. I mean, the price is going up, but you're discounting it. Okay, so running a 0%, is a little bit the same as having an increasing price with the discount factor. And then what you're saying is that you move it from the 8-year to the 12-year. So it's a way to introduce price escalation through the discount factor. Do you understand?
Yeah, I understand, but
Yeah.
I just mean
Yeah.
that maybe, never mind.
Okay, so if we say this is increasing like that, okay, this price increase versus time plus a discount factor of 10% is approximately the same economic model as this and discount factor of 0. I think that's right. Can somebody verify my thinking? Yeah. So if you want to introduce, Michael, like you're suggesting, the price increase, you don't have price increase in your model. This is a simple way to do that. And what you're saying is that when you did that, you actually move this to being 12 years is the optimal. So, right? Is that?
But maybe you can reduce the number of wells by 2, so 12 years with a lower discount. If you just this is the model.
Yeah. Yeah. So I think the bottom line point is that this monotonicity is strongly coupled to the price time variation and the discount factor. So if we build a more realistic economic model, then very well this would not be correct assumption. That we need to keep the plateau time as a variable. I think it's cool. I mean, seeing all of these because when it's integrated, you can start seeing all of these interactions. You may not understand them, but you can see them quantitatively. And the industry does not do this. The industry does not do this, at least in any way rigorously, like we're talking about doing it here. Okay. Any other observations or comments? Yeah.
In all cases, we had the same optimum tubing diameter, and it was the same for those scenarios. With the 150.
Yeah, for your gas in place and permeability. Yeah, that's the same as we saw yesterday. The point is that basically the maximum here for yesterday, yours is a little different today and so forth, that the same optimal 117 for all the cases. I think that's right. I think that, so I think that's a correct observation. Does anyone want to take a guess at why that's the case?
It has to do with this 2.65, the power of diameter to the sea.
I don't know. I mean, certainly, if your A is small enough, okay. Well, the smaller the A. Who had the smallest A of the three groups? You're pointing in the opposite directions. Let's see. Who had the smallest A? Okay, the smallest A was the center group. Okay. What was the tubing? Huh? Was the diameter. Okay. Okay, you all did all three cases? Okay. So let's look at this this observation here. is okay. Let's take our results, and this will be one of the things that we'll see. But I think every group saw that the optimal tubing diameter seemed to be the same. Not the same value as the other group, but this, well, for any plateau time and for any dew point. But yeah, if you take just the vector of tubing diameter, there was a clear maximum at some for all cases. Okay. Okay. Well, let's just take the results here. So this is the group names were. I don't know if we gave them names here or not. Right, center, and left. Okay. We'll take average, average gas in place, and average, and then it was low gas and high K, and high gas in place and low permeability. Okay. Those were the three cases. So let's look at some of the results from those. What I guess we can just start by writing down the values of G, gas in place. So for the average, it was 14. No, 4, 3. 3 10 to the 11. Okay. And for the low, 2. And then 4.5. Okay. And I'm just going to write permeability here. I'm just going to say, I don't know what it was, but I'll just say 500 millidarcies is the base. The base case for A, and then the high K that was 2 times higher. The A value, 2 times higher. A half, yeah. So it'd be Darcy and 250. All right. Okay. So then, with all the assumptions, the optimal plateau was 8 for everybody. Okay. And the tubing diameter for the average group, 115. That's close to yesterday. Was 150. The high permeability should be larger. Okay, that makes sense. Mike Petkovich wouldn't have to, in his deepest sleep, would say not just higher, but he would give you the number. I have to tell you a story about Mike Petkovich. We were doing a project on a Pakistani, a very unusual gas condensate reservoir. It was a single porosity fractured reservoir, and for a project for Occidental, Oxy. We were doing a PVT study, but they sent us all of the production test data because we wanted to see the GOR variation during the production test. So we got the rates and the flowing tubing pressures together with the GORs and stuff. And Mike Vetkovich was visiting, holding with me a course about gas engineering here at the university. He was here for about 6 weeks, I think. And I went in to pick him up. Every day I picked him up at Nardo and brought him in. I said, Mike, we got this interesting, single porosity fractured Pakistani gas reservoir. We're doing a study, and they sent us some multi-rate test data. And he said, well, did you look at the back pressure curve? Of course, I knew I had to do that before I picked him up in the morning. He wasn't even involved in the project, but I knew he would only ask about one thing, the back pressure plot, the log plot of rate versus delta pressure square. So I was so proud. I was so proud I was ahead of him. Sure I did. He says 0.5 slope. And I just kind of slept, 0.52. was the slope of this back pressure curve. It just came out of him like that immediately, because everything is non-Darcy flow. I mean, I probably should have thought about it, but it was just, to him, it was immediate. It was this cause and effect. So he would have immediately picked up that. The higher the permeability, the bigger pipe you generally want to put in there. Although there's a cost associated with the diameter that's in this project, which is not. So 142. And then for the low K, 93. Okay. So this is in millimeters. And then the temperature DPC for the average.
So mine JP
Okay.
is the best one, but then
What we want to do here now is I want to, outside of 80 and then there's minus 40, I want to put both values of NPV.
for 80 it is 9.77, 10 to the power of 9,
Okay.
and for the other one 9.5, 10 to the power of 9.
Okay. Okay, what about the high permeability?
For 4.05, was 10 to the power of 9, and for minus 40 was 3.38, was 10 to the power of 9.
Okay. And the low permeability, high volume?
We have for 80, 1.6 to the power of 10,
1,
0.6,
okay, 16 point,
yeah, 16 to the power of 9, yeah.
16.0, okay, 10 to the 9, and minus 40,
and 16.6.
okay. Okay. So it's almost proportional with gas in place, which you kind of would expect, right? But I'm not sure exactly what it looks like, but it should eventually it should become, if you go out towards infinity, then of course it will become proportional, I think. But the lower the gas in place gets, how should it look? If this is, it shouldn't go to 0 here. Let's see here. Yeah, that's right. That's an extrapolation there from the highest, let's say if you went to very large values. So that's kind of, these are cases we didn't run, but these are like monster, cases. That's kind of the asymptote. I suspect that if you get to low enough G, this has to go to 0 down here somewhere, don't you think? Because you've got all this infrastructure cost and stuff that, you're not going to make enough gas. So this is going to have some kind of shape, probably like that. I'm not sure where we are on this curve, whether all 3 points are on more or less the straight line or it's, but I think it has to be a little bit lower because it's not a doubling here. So, let's see here. Actually, the 16.4, yeah, I'm not sure what it looks like. This is my guess, but we should probably plot it. Okay. Any other results that we should look at?
We found the saddle of where the optimizer goes to plus 80 and minus 40.
Oh, okay. That was for which the right.
The right one.
Okay.
And it actually,
I'll say DPC star. Okay.
and it's around, what is it? 0.2, 0.3. So when I enter these two values, it doesn't optimize everything.
From what was it? Point.
0.2 and 0.3 temperature, dew temperature.
About 0 then.
Yeah.
Okay.
And the time is -2 and 3
For which one here?
for the
Yeah, the first one.
-2.
-2.7399.
Oh yeah, that's we don't want so many digits. Just -2.5. Close. Okay, close to 0, but a little bit colder. Okay. So it actually got there and it couldn't move, even though you included all the variables. Okay.
So we try different solvers to take it.
Right. Right. Okay. Any other observations that you made about it? Okay, so we've got somewhere between 3.5 and 16-ish. Let's put it in from 35 to 160. No, that's 10 to the 9th here. Okay. 3.5 to about $16 billion dollars, the net present value. That's the uncertainty based on our model, based on the uncertainty of gas in place, and based on the uncertainty of the permeability variation. The second is this dew point controller, yes or no. Did the groups discuss that? Which one you feel makes most sense to recommend, or do you have?
For 80 degrees centigrade, we also have to maybe build some gas as well, but I think we don't consider anything in this regard.
But you're.
Consider burning some gas just to decrease the temperature.
Well, you're going to burn gas for what purpose?
Due to controlling the temperature, but 80 degrees centigrade, it's
Well, that was the separator temperature, so it's there. Yeah, that was the separator temperature. It's kind of high, but there's no real costs there. One of the problems with the economic model I see is that the dew point controller in purchase cost should have been 0. You know, at 50 degrees or something. I mean, you basically you're not doing anything going from 80 to 50 degrees. There's some temperature range where there's no effectiveness, so it should have just been you wouldn't put in a dew point controller at a higher temperature than that. So that's okay. Well, you know, what I, instead of just letting this be a soft decision, okay, you know, we talk to the business development people and we sell them on the idea that, well, maybe in the future some new gas fields will come in and we'll process that and we'll make money, okay? Instead of it being one of these soft, if you're a good talker, you can sell it, you know, yes or no. Instead of being it that way, what I would prefer is a strategy, if we can think of one, is to add an incremental net present value to what we have, based on whatever you want to call it. What would you call that? Satellite fields or future external processing? Yeah, asset tie-ins. Yeah, with a question mark of how much, when, and so forth. Okay? And then try to assess a range of volumes and time frames when that could happen. Okay? As early as 5 years, maybe as late as 20 years. As small as 1 TCF, as large as 5 TCF. Okay? Put in some realistic numbers. And the reason I say that is that you basically have this tie-in time, you have the rate going through, and maybe this fraction of NGL would be different for the different fields, things like that. Because if for a realistic set of these, the delta NPV is small, you don't have much of an argument, even if you're a good talker. Okay? Or maybe you'll see that for the most pessimistic assumption, half a TCF in 10 years, that it still turns the table, you know, towards having the unit there. So the best way would be to actually modify the model, add these asset tie-ins, bring it in, and add it to the NPV. That would make the most sense, I think. Yeah.
Up again, that the difference between -40 and 80 for the two cases.
Yeah. Mm-hmm.
See that there is one case that with -40 you get more oil. In the other two ones you get less oil. If you change from 80 to -40, means like the influence of the difference.
Here it's going down.
So you're decreasing.
Here it's going down.
There you are increasing. Yes, like if you put the
Okay.
you get some money.
Okay.
So then the next question is how long the BTC will pay to get that money, and comparing the cost of the BTC itself, and if this difference pays the BTC. And the other cases, you see that even decreasing.
Well, but the DP cost is included in the model now. You know, these are profits in a sense, before tax and royalties.
Okay, if you put like the cost of the BTC, like the infrastructure cost,
Yeah, yeah.
the BTC is inside, there is a
Yeah, that's in the sheet here. I think it's. I think it is.
Yes, it's round and
okay, yes, yes.
Yeah.
Cost.
Here. Yeah.
only thing that's even than 80 degrees that you have some.
That's right. Yeah. So that should have been.
This can help us to say that with BTC you're going to have more money if you in the third phase. Really your OPEX is also included, everything. Why not? You're going to have more money.
Well, you know, the differences are so small. I mean, at least for the first case, it's like 3 out of 9. You know, it's a 3% difference. So with all the assumptions, we've got 3% plus minus. You know, it's almost the same. Here, likewise, it's essentially the same. It's 2.5%. Yeah. This one's a little bit bigger. This is.
Everything, your OPEX is there, and if you really like
Yeah.
that, it's normally.
Well, yeah, but I think that one has to take the numbers with a grain of salt. You don't want to go to the bank with these numbers. These are first order numbers, okay? And the uncertainties in the first order is larger than the differences almost. But so anyway, yeah, I think this is pretty much. And the other thing that we have is that this we observed is very dependent on the probably also on the NGL pricing and discount factor combination. This number is probably 10%. That's probably what the company uses, 8 or 12%. That's okay. But definitely it's dependent on these assumptions here. So okay. I think that's pretty much everything that wanted to. I mean, unless you have any other questions or comments, I think this exercise is. Did it become better? I mean, more understandable than yesterday when you, yeah, working through it yourself and okay. Then, okay. All right. Are you interested in doing this, what you want to do now, or not?
Well, I can, in a few minutes, I can show some overhead that explain the refrigeration system that we use in the field.
Yeah.
Take a couple of minutes.
Okay. Do you want to do it on your computer and I disconnect this?
I'll,
Okay.